Welcome to our video exploring the buffer overflow problem that exists in the C and C++ programming languages. To begin, we're going to introduce you to what a buffer overflow is and explain the mechanics of how they can be exploited. Later, we'll apply this in a demonstration of an actual stack buffer overflow exploitation. So first, let's define what we mean by buffer and buffer overflow. According to Wiktionary, a buffer is a portion of memory set aside to store data, often before it is sent to an external device or as it is received from an external device. In this video, our definition is a bit more specific. We're talking about a C-style string or a null-terminated char array that is used to receive keyboard input. The term buffer overflow refers to writing data to a buffer where the size of the data exceeds the boundaries of the buffer, causing the memory adjacent to the buffer to be overwritten. As a quick demonstration of why this is obviously a bad thing, consider the following C program. We're copying a 26-character string into a char array of size 4. The char variable C is initialized with an uppercase A and is never changed within the source. Now, different environments and compilers will give different results, but when we run this code in Visual Studio and the value of C is printed to the screen, it prints C is P. This is because the strcpy function overwrote the location of C within memory. It's not until the program is finished executing that we get an error message. It says stack around the variable buffer was corrupted. The stack it mentions is the call stack of our program, which we'll be looking at in more detail a little bit later. So why is it that buffer overflows can happen? C and C++ provide no inherent built-in protection against accessing data in any part of memory. As a result, library functions such as scanf, getS, strcpy, strcat don't actually check that the size of data they're writing is within the boundaries of the destination string. When a buffer is overrun, the memory adjacent to the buffer is overwritten. Now let's change our example program from copying a string to getting one as keyboard input. And instead of changing C to P, let's change C to an exclamation mark. And that works. This is the basic mechanism behind buffer overflow exploits, using input to overwrite targeted areas in memory with the data we specify. The next step to understanding how we can exploit this technique is to understand the architecture of the memory stack at runtime. Let's start with a big picture of what a program looks like in memory, building from higher memory addresses to lower memory addresses. We have a stack offset, the stack which grows up into lower memory addresses, a memory offset for stack growth, the memory map segment, a memory offset for heap growth, the heap which grows down into higher memory addresses, the BSS segment, the data segment, and the text segment, which is where our code is stored as executable instructions. Also, the system provides several registers to the program that are used to store data within the CPU. As we take a closer look at the call stack, the registers we need to know about are the instruction pointer, the base pointer, and the stack pointer. The stack frame, like any stack, is a last in, first out structure. The stack grows as we push items on top, and the stack shrinks as we pop items off the top. The call stack is composed of stack frames for every function that's been called but is not yet returned. Each stack frame includes the parameters passed into the function, the return address pointing back to where the function was called, and the local variables inside the function. The first stack frame for any program is always our main, and with each function call, a new stack frame is pushed onto the stack and the registers are updated. The instruction pointer will naturally point to the first instruction that gets executed inside the called function. The stack pointer will now point to the top of the stack, allowing the program to know where to push the stack frame for the next function call. The base pointer will point to the return address stored inside the stack frame. The return address is actually the address of the next instruction that will be executed inside the calling function once the called function returns. When the function returns, the registers are updated again and its stack frame is popped off the stack. The stack pointer will now point to the new top of the stack. The base pointer will point to the return address in the calling function stack frame, which is now the top of its call stack. Finally, the instruction pointer will be updated with the return address inside the stack frame that is being popped. That last step is the key to stack buffer overflow exploitation. What happens if we use the buffer overflow to overwrite the return address with a different address? We can actually force the program to execute the code at any location we want it to. To see this in action, here's Dan with a demo.
Hey everyone, today I'm going to show you a demonstration of buffer overflows and how we can use them to our advantage. If we go ahead and open up this folder here, I've got a buffer overflow program that I wrote. Here's the code for it. Start of the main function, calls the getInput function, which is up here. Then it declares a char array of 20 characters called buffer, asks the user to enter the code, and then receives the input into buffer using gets. Okay. Doesn't really do anything with that after that though. It just exits and then returns 0 and then program ends. Our goal is to use buffer overflows to extend this 20 character char array and input a particular code that will actually cause this function to get executed. And we can actually do that, and it's not even too difficult. What we're going to do, actually, I'll show you this first. So if we put in any code, whatever, it just quits. But if we put more than 20, it crashes. Now, if we look at the error report, this doesn't really help us much. This error report here, it doesn't really say too much about what we inputted. This doesn't really relate to the code at all. But that's because when you compile a program, Windows actually has built-in protection, and Buffer Overflow is one of those protections. We have to get rid of that protection first. So let's go ahead and open up Ollie Debug, and this is a cool program where you can disassemble any exe. And so here's the disassembled code for it. And if we scroll around, we should find our functions. They're up here. So here's our function. So here's the operation hijack function, which never gets called. And here is the enter code function. This is the get input function. Okay. Now I've put a breakpoint here. This call here, this is the call to gets, and this is the call to printf, right? So we're basically saying, okay, put this string onto the stack and call printf. Then we do some stuff here. Then we go ahead and do the same thing, but we just call gets, okay? And then we receive gets. Now what happens, what actually happens here is when it receives the input, it checks to see if it's actually more than 20. It checks to see if we've overflowed. And if we have, it's going to call this function here. This is what actually causes Windows to crash and say, whoa, there's an overflow. I'm going to deal with it here before we do anything bad. Now, our goal is to actually get past this, and if we overflow the buffer, we can actually modify where the function returns to. And this is good. So, but what we first need to do is I'll run the program, and running the program, it's sitting there, it gets, it's sitting here, waiting. So I'm going to put in some input. I'm going to put more than 20. If I enter, you can notice that we can actually step through a program, and here, it actually does get to this line of code, which gets us completely somewhere else, and if we keep trying to run the program executes. And there is an error code, so it does crash, okay? So that's bad. That's not what we want. So if we actually open up the program again, the cool thing about this Ollie debug is that you can actually assemble. It's not just disassembler, you can actually assemble and modify the exe. So we don't want this to happen. This is the built-in protection. We don't want it to happen, get rid of it. So I'm going to go ahead and hit space and just fill it up with nops, which basically just do nothing. So if we assemble that and we go ahead and run it this time, I'm going to input some more random crap. And stepping through it, you'll notice it just goes through the knobs, and then we can actually continue on our normal execution. Okay, so that's good. Oops. So that's good there. It's going to keep crashing, and I'll explain why in a second. But what the best thing to do here is if we open up this again, and we've got this, we have to fill it in with nops again. What we're going to do is we're actually going to assemble this into a new executable. So we're going to take this, right click, and go ahead and do copy to executable, copy the selection, and when we close it, it'll ask us to save it, and we're going to save over top of this BOF. So do you really want to overwrite it? Yes. Now if we close this, open it up again, and open up the same BOF, which is actually our modified one now, you'll notice that this is built in now. So there, we've overridden Windows's protection. Now the next step is to actually do something smart with the code that we input. So here's what I'm going to do. Come over here to Buffer Overflow, and I run it, and I go something crazy. Check the error report. Now this looks different, and now this is actually good. We've got an offset here, and this is the offset that caused the issue. Basically, at what memory address did we crash at, or do we not know what to do at? And that's this memory address here. Now this looks weird, but it's actually meaningful, and I'll show you why it's meaningful. If we actually input something a little bit more readable, let's do 20 characters of A, B, 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 and so on. There's 20 characters. Then I'm going to go A, B, C, D. If we go ahead and hit enter and look at the error report, here's the offset that we're crashing at. And it's actually 64, 63, 62, 61. Now 61 is ASCII for lowercase a, 62 is ASCII for lowercase b, lowercase c, and lowercase d. Now, two things to note about this. First of all, this is actually smart. This is actually the ABCD that's here. The other thing to note is that it's actually backwards. Okay, and that's something that we're going to have to deal with. Basically, the code that it tries to jump to is going to be the backwards ASCII value of these here. So the 61, 62, 63, 64 is A, B, C, D, which are these four here. And that's good. That means it tried to jump to this A, B, C, D backwards, and it didn't know what to do. Obviously, at this memory location, there's going to be garbage. It's not going to be a regular program execution necessarily, so that's why it crashes. So we're going to use that to our advantage. Knowing that, I'm going to go ahead and put a breakpoint here, and let's go ahead and run it again. Now we're going to go ahead and do the same thing. A, B, C, D. Enter. Now if we step through it, you'll notice our stack down here. Our stack holds what we inputted. Okay, here's our 61, 62, 63, 64. These are the 4 A's, 4 B's, 4 C's, D's, E's, F, G's, and then the A, B, C, D that's backwards. Okay, so if we step through this, you'll notice that once we move the stuff and we pop off the stack, we try to return to this memory address, and that's why it crashes. So what we're going to do is we're going to modify it so that the code that we input actually gets us to get over here. Now you'll notice we have a 0, 0 afterwards. That's fortunate. That means that if, for example, the code, the memory address up here is 00401000, there's no way to actually input a 0, 0 in ASCII because it's null. So that's a problem that you're going to face, but we can get around that. The good thing is that we have a 0, 0 at the end here afterwards. So if we only put in 3 characters, there's going to be a 0, 0 there, which if we reverse it is going to be the first 0, 0 here. Now here's an issue. There's also a 0, 0 at the end. So to get around this, we're actually going to add a little bit more to this program here. Okay, we're going to go down here to just over here, and we're going to assemble something here. I'm going to go ahead and do a call to bof.00401000. Enter. Oh, sorry, the bof dot is extra. I don't need that. If I go ahead and hit enter, then this line of this memory address here is actually going to be a call to the start of our operation hijack function up here. 00401000. There it is. Then we have to assemble a return so that it doesn't completely get lost and crash. So what I want to do is I want to input a code that where the last the last 3 characters that we input are going to be the memory address of 00401058. If I do that, this return should jump here, which will then call this memory address. This will get executed, then it'll return, and then it'll return. So it's kind of like making like a long cut. Basically, we're just executing this, and then the program will continue on its regular execution. This is pretty cool stuff. What I'm going to have to do though is I'm going to have to copy this into the executable here, and then do the same thing. Yes, copy it over, and let's actually make sure it's there. So that's the cool thing about Ollie Debug. You can actually change programs. And if I open this up, scroll all the way up, there is our call here. Now this is essentially a goto, and I know Carlo doesn't like gotos, but it actually works here. So sorry, Carlo, but this is useful. Now the next step is to know what code that we input is actually going to get this memory address to be called. For that, we're going to need a calculator and Notepad. Okay. The idea behind this is that we need to use the ASCII values of these values here so that we know what to input. Now, another thing to remember is that we have to reverse it at the end. Okay. But what I'm going to do is I'm going to go to hex here, and I'm going to take this memory address. So 00, obviously, this is the address here, 00401005, oh sorry, it's 58. So let's go ahead and space this out a little bit. So that's what we want. So if we take, obviously 00, we can't do 00, so we're going to just leave that as it is. Now if we take 40 in hex, 40 in hex is 64 in decimal. So this is 64. 10 in hex, well that should be 16, yeah. 16 and 58 in hex is 88 in ASCII. Okay? So now I'm also going to need the help of this here. This is going to allow us to input these particular ASCII codes so that it gives us a one-character representation of it. So again, 00 is going to stay as it is. Then we need the ASCII value for 64. Actually, let's go ahead and reverse this right now. 88, 16, 64. So we need the ASCII value for 88. So if we go ahead and do Alt 88 and then release Alt, it'll give us, oh look, it's a capital X. That's what the ASCII value of 88 is. So there it is. Now we're going to go ahead and do 16. So Alt 16, release Alt. That's cool. And then Alt 64, release Alt. And an @ sign. Cool. So this is the code that we need to input. If we put this at the end, this is already reversed, so the 00 is actually going to be over here. And since it's already there, we're fortunate in that sense. This is the last 3 characters that we have to input. So let's go ahead and copy that. And this should be the representation of this line of in our memory here. And then it'll essentially call this, and we should get our operation hijacked. So let's go ahead and put a breakpoint. I'll put a breakpoint here so that we can just stop it afterwards. And we should go ahead and run our program. And we're going to do, okay, so we have to do the 20 first. So there's 20. Now I'm going to go ahead and copy that code that we got. So let's paste that there. And then if I input nothing afterwards, it'll be the 00 that we saw over here. And this should actually get us operation hijacked. There it is. So essentially we used ASCII characters and to input a particular code that allowed us to modify the execution of the program. And this is the beauty of buffer overflows, and this is why they're so important and why they're so dangerous at the same time. If this was a function to give me like infinite lives in a game, and it was this easy to crack and to create a buffer overflow like this, then you could see what power you have once you're able to modify and use buffer overflows to your advantage. All right, so there it is. There's the little demonstration there. So thanks for watching the video. Hopefully you guys learned something new today, and we'll see you next time.